A very good day to Inche Moma. It's me Aswali bin Harimi. So this is our end of chapter assessment from us, Emida, Dingesora and Giovanni.
Hydroelectric installation classified by the infection head of water. This is the type of installation commonly in use with the turbine sample for each installation, as well as one suitable turbine runner according of each installation type. Okay, first, high head hydroelectric plant. Power station operate under head above 300 meters. In this type, power plant, the water flow through the turbine originate from a significantly high elevation, which reduces the same amount of water required by the system to generate the same amount of energy. Suitable turbine, Pelton Wire turbine. Okay, second, medium high hydroelectric plant. Power station operating above 330 meters to 300 meters. The power station less height drop in the medium head dam than in high head dam. The pen stop is little bit shorter. A substantial amount of water must flow and the water height must significantly increase for the short of them to function. Okay, suitable turbine, Francis turbine. Third, low height hydroelectric plant. Low head hydroelectric developed through definition vary. Refer to creation of hydropower, then the height is typically than 20 meters. Head of the distance in vertical height between the water level at the hydro intake and the water level discharge point. Suitable turbine, Kaplan turbine.
A very good day to everyone. I'm Lingeswara, son of K. Lishmanan. My matrix number is 01DE20F2042. Today I'm going to explain about question 2. So that is discuss two potential of hydroelectric power plant in generating grid scale electricity supply and two environmental impact of hydroelectric development by referring to a real power plant example that have been previously reported in Malaysia. So this is the Chendero hydroelectric power plant. So now I'm going to explain about Chendero Power Station. So Chendero Power Station or Chendero Dam is one of the oldest and the first major hydroelectric dam and power station in Malaysia. It was preceded by two earlier boys. So power station. The power station is a hydroelectric power station using 4 turbines of 10.7 MW and one of the 8.4 MW, totaling is 40.5 MW installed capacity. The station is operated by Tenaga Nasional. So and then the Chendero Dam technical specification. The permanent and dam component are as follows. Main dam. Crease elevation is 50 meters, 160 feet. About sea level is ASL. Maximum flood level is 48 meters, 157 feet. Operating level maximum 45 meters. Reservoir area is 45 meters, 148 feet. ASL is 25 square kilometer, 9.7 square MIN with catchment area of X 000 kilometer. Clarification needed. Storage volume is 95 million cubic meter, 3.4 times 109 cubic feet. So power intake structure is 5 bays, spillways, gated concentrate gear with chute and flip bucket. Power tunnels, 5 tunnel. Powerhouse with 5 pentugs to power train comprising 5 turbines of 10.7 MW each, and one of the is 8.4 MW generating of 15 MVA each, and 4 transformer of 15 MVA each. So next is two potential of hydroelectric power plant in generating grid scale electricity supply and two environmental impact of hydroelectric development by referring to Chendero hydroelectric power plant that have been previously reported in Malaysia. So first is the potential of hydroelectric power plant in generating grid scale electricity supply is divided by 3 that is small scale hydroelectric. The second is mini scale hydroelectric and third is micro scale hydropower. The first is small scale hydroelectric is generated electric power of between 100 kilowatt and 1 megawatt. That site is chosen for as HP is usually rivers or streams. It is called a run of the river system. Fluid flows or the expected maximum water level is needed to a size spillway if any. The statistically disruption of monthly stream flow volumes. So next is mini scale hydroelectric, a scheme that generates power between 5 kilowatt and 10 kilowatt, feeding it directly into the utility grid or as a part of battery charging or AC power stand-alone system. So last is micro scale hydropower, small homemade run river type scheme that use DC generators designed to produce electrical power between a few hundred watts up to 5 kilowatt as part of the battery charging stand-alone system.
Hi, I'm Giovanni. Now we are going to talk about question 2b, environmental impacts of hydroelectric developments. First is advantage hydroelectric power plant. So renewable. Hydropower is completely renewable, which means it will never run out unless the water stops flowing. As a result, hydro plants are built to last. In some cases, equipment that was built to the last 25 years is still operational after double the amount of time has passed. Second, emission free. The creation of hydroelectricity does not release emissions into the atmosphere. This is of course the biggest appeal of any renewable energy sources. Now we are going to see disadvantages of hydroelectric power plant, which is like impacts. First is impact on fish. To create a hydro plant, a running water source must be dammed. This prevents fish from reaching their breeding ground, which in turn affects any animal that relies on those fish for food. As the water stops flowing, riverside habitats begin to disappear. This can even remove animals from accessing water. The turbines kill some fish that pass through them. According to the Energy Information Administration, 5% to 10% of fish deaths are a result of the best turbines currently in use. Limited plant location. While hydropower is renewable, there are limited places in the world that are suitable for plant construction. On top of this, some of these places are not close to major cities that could fully benefit from the energy. Third, flooding. The unstreamed flooding caused by the dams used for irrigation, flood control, and hydropower generation can be harmful to native plants, wildlife habitats, significant natural areas, agriculture land, and people. Such flooding events may completely engulf people's homes and force them to evacuate. And next, now I'm going to talk about question 3. By considering the technical aspects below, demonstrate the principle of hydroelectric in electricity generation with respect to. So this is the picture. hydroelectric power P, since and energy, PHQ is N is efficiency, 9.81 is the gravity. So this is example of dam, the picture of dam. So now let's talk about first generator frequency and voltage control principle. Hydroelectric power plants generate electricity by using the kinetic energy of falling water to drive a turbine, which in turn drives a generator to produce electricity. The frequency and voltage of the generated electricity depend on the rotational speed of the generator. The generator voltage and frequency must be controlled to ensure the stability and reliability of the grid. This is achieved through the use of automatic voltage regulating AVRs and governors. The AVR controls the generator output voltage by adjusting the field current of the generator, while the governor controls the rotational speed of the turbine by adjusting the flow of water to the turbine. By maintaining a constant rotational speed, the frequency and voltage of the generator electricity can be controlled within the acceptable range. The magnitude of the voltage produced by a synchronous generator is proportional to both the generator speed and the generator field current. Now next, generator synchronization using a synchro check relay. A synchronism check relay provides a contact closure when the frequency and phase of two sources are similar to meeting some tolerance margin. The relays are generally used when there is a need to connect two or more systems to single line. Before a generator can be connected to the grid, it must be synchronized with the grid to ensure that the frequency, voltage, and phase angle of the generated electricity match those of the grid. This is done using a synchro check relay, which compares the voltage, frequency, and phase angle of the generator with those of the grid. When the parameters are within the acceptable range, the relay closes the circuit breaker and connects the generator to the grid. Third, generator operation with speed and voltage regulation. The voltage regulation of an alternator or synchronous generator is defined as the rise in the terminal voltage when the load is decreased from full load rated value to zero. The speed and field current of the alternator remain constant. In other words, the voltage regulation of the alternator can be defined as the change in terminal voltage from no load to full load rated value divided by the full load rated voltage. The voltage regulation is like the figure of merit of an alternator. The generator speed and voltage must be regulated to maintain the stability and reliability of the grid. The speed is regulated by the governor, which adjusts the flow of water to the turbine to maintain a constant rotational speed. The voltage is regulated by the AVR, which adjusts the field current of the generator to maintain a constant voltage output. By maintaining a constant speed and voltage, the generator can operate within the acceptable range of the grid. For an ideal alternator, the value of the voltage regulation is zero. So this is an example of image transmission line. Now for fourth part, generator speed and voltage regulation with group. Group speed control is a control mode used for AC electrical power generators, whereby the power of output of a generator reduces as the line frequency increases. The generator speed and voltage regulation can also be achieved using group control. Group control adjusts the speed and voltage output of the generator in proportion to the load on the generator. This means that as the load on the generator increases, the speed and the voltage output decreases slightly. This ensures that the generator shares the load with other generators on the grid and maintains a stable frequency and voltage output. It is commonly used as the speed control mode of the governor of a prime mover driving a synchronous generator connected to an electrical grid. It works by controlling the rate of power produced by the prime mover according to the grid frequency. Fifth, generator parallel operation and load sharing. In a hydroelectric power plant, multiple generators can be connected in parallel to the grid to share the load. The generators must be synchronized with the grid and have similar frequency, voltage, and phase angle parameters. Load sharing is achieved using group control, which adjusts the speed and voltage output of the generators in proportion to their load. This ensures that each generator shares the equal and maintains a stable frequency and voltage output. This synchronization and load sharing are typically controlled by a supervisory control and data acquisition SCADA system, which monitors and controls the operation of this generation. For two or more generations to operate in parallel, the following conditions usually must be met and maintained. Waveform must produce adequate sine wave. Phase sequence, order which voltage peaks are reached on the sine wave form must match. Frequency, time it takes for one positive and one negative peak on sine wave form must match. Phase angle difference in phase angle between two sine waves must not exceed established value in a three-phase system. Voltage amplitude difference, sine wave voltage peak must match. When generators are operated in parallel, many configurations can be utilized. Therefore, 2 kW parallel with 2 kW equal 4 kW capability. Thank you.